Okay, good morning, dear students. Today we will solve an example of uniform convergence of a sequence of function. Convergence of sequence of function. Okay, and with the help of this theorem, the theorem is let f(n)x, this is f(n)x, be a sequence of function such that fx equal to limit n tends to infinite f(n)x. This is the process for finding the pointwise limit at x belongs to 0 a to b, and let mn is the supremum x belongs to a to b is the fn(x) minus fx. Then always fn(x) tends to fx uniformly on a and b. If mn tends to 0, this is very important, when mn tends to 0 as n tends to infinite. Okay, for example, fn x equal to x upon 1 plus x square, 1 plus nx square, x belongs to the real number, converges uniformly on any closed interval I. Okay, and the question is proved that this is uniformly convergent on any closed interval I. For finding the uniform convergence of this sequence of function, first we need to find fx. This is the fx equal to limit n tends to infinite fn(x) equal to n tends to infinite x upon 1 plus x square. And for any x, suppose that we put x equal to 1, 2, 3 and any real number in at the place of x in this function, and when n tends to infinite, then always this tends to 0. Okay, the limit of this function is always equal to 0. Clear? This is the limiting function. It means the limiting function of this function fx equal to 0. This is the limiting function. Clear? And according this limiting function, because the limit is exist and this is 0, this function fn(x) is pointwise convergence. It means it is converges at each and every point in the given interval I. Okay, and for finding the uniformly convergent, first we need to find mn for this sequence. Mn equal to supremum x belongs to I, fn(x) minus fx, because the fx is equal to 0. This is the limiting function, and so it is equal to supremum of x belongs to x upon 1 plus nx, because this value minus 0, it is equal to this. Okay, now for finding the supremum value of this at any integer x and at any interval I, first we need to find the supremum value of this function. For finding the supremum value, we can take this. Suppose that this is fn(x) equal to x upon 1 plus, or we can write it mn or any function. Suppose that this is y. This is y equal to nx square, and we know about the process for finding the maxima and minima and the supremum value of any function by first we differentiate this dy upon dx. It is equal to 1 plus nx square to the power 2, and in numerator 1 plus nx square, and differentiation of this is 1 minus the second, this is as it is, and differentiation of this is 2nx. This is 2nx. Okay, and it is equal to 1 plus nx square minus 2nx square upon 1 plus nx square to the power 2. Okay, we know about the maxima and minima. For finding the maxima and minima, always dy upon dx equal to 0. dy upon dx equal to 0. This is equal to 0. When you take this is equal to 0, then this is equal to 0. Clear? When you take this is equal to 0, then denominator part equal to 0 and the numerator equal to this numerator equal to 1 plus nx square minus 2nx square is minus nx square equal to 0. Right? And the value of x is the value of x is x equal to n x square equal to 1 and x equal to 1 plus minus 1 upon under root n. This is the value of x. It's mean at x equal to plus minus 1 upon root x, this function has any maximum value. Okay, and the maximum value of this function is when you put x equal to this at the point of at the place of this, then the maximum value is 1 upon root n upon 1 plus n, and 1 upon root n equal to 1 upon n. Okay, 1 upon root n square equal to 1 upon n, then this is equal to n, and when we cancelled out this, then this in denominator we have 2, and the answer is this is equal to 1 upon 2 root n. Okay, it's mean the maximum value of this function at x equal to 1 upon root n is 1 upon 2 root n. This is the maximum value. It's mean the supremum for any x of this function, or the supremum for any x of this function of this sequence, it is equal to 1 upon 2 root n. This is the maximum and this is the supremum. Okay, now we have the n. What the value of n? N tends to infinite. It's mean when we take the limit on this function, n tends to infinite, then it is tends to 0. It is equal to 0. Okay, when n tends to infinite, then this is equal to 0. And our theorem is fnx tends to fx uniformly, okay, on a to b if mn tends to 0 as n tends to infinite. Okay, so here n tends to infinite, then mn tends to 0 for any supremum value of this. Okay, mn tends to 0 when n tends to infinite. In this case, this is uniformly convergent and also pointwise convergent. Okay, okay, this implies f and x is uniformly convergent. Okay, and convergent. Okay, and we know about the rule of the uniformly convergent sequence. Always a uniform convergence sequence is a pointwise convergence sequence. Clear? And also if fx exists, fx equal to limit n tends to infinite, f and x exist, then always this sequence is pointwise convergence. And this sequence, if the sequence is uniformly convergent, then sequence always pointwise convergent. Okay, students, this is the example with the theorems. Thank you.